The internal combustion engine is the heart of Kawasaki's complete line of products. And the engine's ignition system is the pacemaker that keeps it beating thousands of times a minute, year after year. In this videotape, you'll learn about the different Kawasaki ignition systems and how they work. And you'll see how the different systems apply to differing products and a little bit about why. Any ignition system must perform three basic jobs for the engine. First, it must produce a large high-temperature source of heat. Second, it must deliver the heat at just the right time to produce fuel-efficient power. Finally, it must protect the engine from damage at low speeds and also at high speeds. Every ignition system has the same four basic parts. It must have a spark plug. It must have a way to convert low voltage electricity to high voltage. It must have a power source. And it must have a switching device to turn on the spark. Let's start with the basic ignition system. The boxes represent the four basic parts which every ignition system must have. The lines connecting them are the wiring. The spark plug has two electrodes insulated from each other. If a high enough voltage is applied to the electrodes, a spark will leap the gap between them. The coil is actually two coils of wire wrapped around each other. One wrapping, called the primary side of the coil, has relatively few turns of wire. The other wrapping is called the secondary side. It has thousands of turns of wire. The ratio of turns between the primary and secondary determines how high the voltage is that the coil can deliver to the spark plug. If the ratio is 10 turns to 10,000, the voltage will be multiplied 1,000 times. 12 volts at the power source become 12,000 at the spark plug. The power source for the coil can be a battery or a magneto, which is a type of alternating current generator. The switching device turns the power going through the primary side of the coil on and off. Now here is how the parts work together. The power source, a battery, sends an electric current through the switching device and the coil and back to itself, slowly building a magnetic field in the primary side of the coil. When the switch, a set of breaker points in this case, is opened by a cam, the current stops flowing through the primary side and the magnetic field it built now collapses. The collapsing magnetic field passes quickly across the secondary windings of the coil, creating in them a very high voltage. And if the voltage is high enough, it jumps the gap of the spark plug and ignites the mixture in the engine's combustion chamber. This system is called battery coil ignition with breaker points. Okay, now that we have seen how the battery coil system provides ignition, how does it do the second job, timing? The cam that opens the points turns with the engine. Every time it goes around, it opens the points and sets off the spark. If the cam is mounted on the crankshaft, it's going to send a spark to the plug once every engine revolution. This works out nicely for a two-stroke cycle engine. And in a four-stroke, it just wastes every other spark. If the engine ran at a single speed all the time, this simple ignition system would be almost ideal. But no motorcycle engine ever runs at a single speed for very long. And as the engine speed changes, the ideal moment for ignition to occur changes as well. The faster the engine runs, the earlier the spark must go off to allow time for the mixture to burn. One way to advance the moment of ignition timing is this mechanical advancer. It has weights that move outward under centrifugal force as the engine accelerates, turning the cam relative to the crankshaft, so it will open the points sooner. Springs control the movement of the weights and return them to their rest position. The mechanical advancer fits into the battery coil ignition system like this. Because the points in this system are mechanical, they are subject to wear and must be adjusted, cleaned, and eventually replaced. To eliminate the maintenance needed by the breaker points, a transistorized version of the battery coil system uses an electronic sensor called a pickup coil. A new component, the igniter unit, gets the electronic signal from the pickup coil, and a transistorized circuit inside it does the actual switching. This variation of the battery coil ignition is called transistor-controlled breakerless ignition, or TCBI. Instead of a cam, a small projection called a reluctor rotates on the end of the crankshaft and induces a current in the pickup coil as it goes by. The current travels to the transistorized circuit inside the igniter, which switches off the power to the primary side of the coil. This early version TCBI uses a mechanical advancer that works exactly the same as in a system with points. In this system, it advances the reluctor instead of points cam. But the mechanical advancer unit can wear too. Its springs can weaken with age, and it can stick in one position, throwing off the advance curve. The obvious solution to these problems is to eliminate the mechanical advancer and use an electronic circuit in the igniter unit to do the job. Some electronic advancer circuits use the analog signal directly from the pickup coil to advance the timing. When the voltage of the pickup coil signal reaches a certain value, the spark is triggered. The advancer circuitry in the igniter unit sets the ignition timing according to engine speed. Other electronic advancer circuits use the pickup coil signal in a digitized or squared-off form. The igniter unit has a microprocessor in it, a tiny computer which is programmed with a map of what the ignition timing should be at any engine speed. The digital ignition system can be programmed to follow a more complex curve than an analog system, and it follows that curve more accurately. The pickup coil signal in a digital system is generally far in advance of the maximum advance needed by the engine. The microprocessor actually waits for a specified time after getting the timing pulse to set off the spark plug. It has an internal clock that runs at a very high frequency to time the delay accurately. The systems seen so far have been variations on the battery coil system in which the magnetic field in the high-tension coil collapses to produce the high voltage in the secondary winding of the coil and fire the plug. In the magneto-ignition system used by Kawasaki, the magnetic field in the coil builds up so rapidly that it produces enough secondary winding voltage to fire the plug. Let's go back to the basic ignition system we started with and build it into a magneto system. A basic magneto ignition system is just like a battery coil system, except that instead of a battery, the power source is an alternating current generator made up of a flywheel or rotor and a stator. As the flywheel in the magneto turns, it induces a voltage in the windings of the stator. The closed points short this output to ground so it cannot flow through the primary side of the coil. When the points open, the magneto output suddenly flows through the primary side of the coil, inducing the high voltage in the secondary side needed to jump the spark plug gap and ignite the mixture. This magneto system is simple, rugged, and needs little attention. It is used in inexpensive, lightweight products. The magneto-powered capacitor discharge ignition, or magneto CDI system, is an outgrowth of the basic magneto system. The differences start with the magneto, which has an exciter coil to charge a large capacitor. The output of the exciter coil is halfway rectified because the capacitor needs direct current. The capacitor discharges through the primary side of the coil to fire the spark plug. The switching device is a pickup coil or a pulsar coil and a switching circuit in the igniter unit similar to what we saw in the TCBI system. The output voltage or signal from the pickup or pulsar coil is a sine wave, and the igniter unit discharges the capacitor when that voltage reaches a certain value, the trigger voltage. As engine speed rises, the signal voltage goes higher, reaching the trigger voltage sooner and advancing the spark timing. The magneto CDI system has a very short rise time and produces a powerful spark. That is, the voltage available to the spark plug goes up very quickly to very high values, enabling it to fire under adverse conditions that might foul the spark plugs of other systems. This system is suited to off-road motorcycle use because of its lightweight and powerful spark. The engine is easily kick-started even if the battery is dead. Most off-road motorcycles with magneto CDI systems have no battery at all, making them even lighter and simpler. To better control the spark advance in magneto CDI systems, an electronic advancer may be incorporated in the igniter unit. The advancer can be an analog circuit or a digital one, just like in the TCBI systems. This completes our presentation on Kawasaki typical ignition systems and products. For more details such as specific functions in different Kawasaki products, please watch Part 2.